Imagine a 1 kilometer drag race in the sky. In one lane, a living predator. In the other, a pinnacle of human aerospace engineering. Right off the starting line, the biological bird takes a substantial lead over a machine designed to fly twice the speed of sound. Before the jet has even moved a meter, the Falcon is already plummeting toward its top speed. It's a physical contradiction. We have a bird weighing about 2 pounds out-accelerating a supersonic engine. To find out how, we have to look at the mechanics of that first second. This matrix compares their raw power. The F-16's top speed is higher, but the decisive metrics are thrust source and total weight. Look at the thrust row. By utilizing gravity, the Falcon initiates movement without any engine spool-up time. That creates an immediate advantage in agility. Because the Falcon uses gravity to pull it downward, it achieves instant acceleration. But it also means the bird is mathematically incapable of maintaining that velocity in a horizontal line. By deconstructing the physics of this sprint, we can locate the exact point where biological evolution hits its physical limit and mechanical engineering takes over. At the start, the Falcon dominates the immediate physical response, but as the distance grows, we'll see why human technology is required to break the constraints of sustained physics. To understand the bird's advantage, we start at the perch. From this height, the Falcon holds immense potential energy, ready to be converted into speed at a moment's notice. When it launches, the Falcon doesn't just fly, it drops. It enters a stoop, a steep gravity-assisted dive that serves as its primary hunting strategy. This composite tracks the descent. The Falcon acts as a morphing wing, altering its biological shape. Notice postures A and B. It tacks its wings into a tight V-shape, reducing its surface area and cutting aerodynamic drag. This tight V-shape also reduces roll inertia. That allows the Falcon to make rapid corrections to its flight path while at high velocity. Through this low drag design, the Falcon reaches a peak dive speed of 380 kilometers per hour. These graphs show the forces involved. When the bird pulls out of its dive, it experiences extreme mechanical loads, hitting accelerations of 11.5 meters per second squared as it redirects its momentum. Tracking a target at these speeds requires proportional navigation. The bird's brain calculates a collision course based purely on the change in its line of sight to the prey. But there is a ceiling to this performance. By tucking its wings to minimize drag, the Falcon sacrifices nearly all its aerodynamic lift. Because the bird is essentially falling, its peak velocity is restricted to these short, targeted bursts. It cannot maintain this speed in level flight. In stark contrast, we have the F-16, a dense 14-ton airframe of titanium and aluminum. Unlike the Falcon's instant drop, the jet suffers from a significant mechanical lag. It needs roughly 30 seconds just to overcome its own stationary mass and get moving. To even leave the ground, the F-16 has to reach 225 kilometers per hour. Only then can its wings generate enough lift to support its weight. This graph illustrates the paradox. At 0 seconds, the Falcon moves at high speed, while the F-16 crawls from 0. But once airborne, the jet provides continuous thrust. Its velocity curves steeply upward, crossing the Falcon's declining speed. This continuous combustion is the key. It makes the jet's speed independent of gravity. This allows the F-16 to reach and maintain supersonic speeds of Mach 2.0 while flying horizontally. The trade-off is the vast logistical support needed to make this possible, from miles of concrete runway to tons of specialized jet fuel. The machine lacks the instant agility of the Falcon, but it can maintain its velocity for as long as the fuel in its tanks continues to burn. As the 1-kilometer race ends, the Falcon has to pull out of its dive to avoid the ground, quickly bleeding off its speed. The F-16, now at full power, easily overtakes the bird before the finish line. We map these approaches on an engineering matrix, comparing energy efficiency against sustained speed. The Falcon sits top left, highly efficient using gravity, but limited in duration. The F-16 sits bottom right, inefficiently burning massive fuel, but unmatched in holding high velocity. Engineers use biomimicry to bridge the gap between these two quadrants, studying nature's efficient designs to improve our own machines. This comparison shows how we've adapted biological structures. Birds use separated feathers at their wingtips to manage air turbulence, a technique that provides passive flow control. These low-drag biological shapes led directly to the streamlined, blended wing designs used in aircraft like the B-2 Spirit stealth bomber. We now use digital fluid dynamics to simulate these biological movements, allowing us to build more efficient wings for drones and next-generation aircraft. While we can adapt nature's blueprints to optimize aerodynamic efficiency, our modern aviation still depends on the sheer brute force of mechanical combustion to stay dominant in the sky.